So in this video, we're going to cover a few more alkene reactions. And the first one we're going to discuss is this oxymercuration. And this is kind of like we hinted to with the last video. This is a better reaction to get a hydration product, a better reaction to get OH added to our alkene in a Markovnikov fashion, right? That OH adding to the most substituted carbon. One thing you'll notice here probably right away is that we're dealing with mercury, right? A metal, which we haven't dealt with before in some of these reactions. And what this will kind of lead us to is the fact that the mechanism is a little bit more complicated than usual. So this is going to be a case where we don't need to worry about the mechanism, but I am going to show you to sort of explain what's going on, okay? So just bear with me here for some of these future mechanisms where it's going to look a little weird, but I'll certainly let you know that these mechanisms that we're going to be dealing with are not something you need to be too concerned about, but more so that you recognize, right, the reaction conditions and what the product should be because of it, okay? So the first thing I'll say here also is that this mercuric acetate, you'll also see it in your book written like this, right? And what this molecule actually looks like, just so you know, is something like this. Right, again, with mercury here being a metal, so things are going to look a little bit different when we start doing this mechanism. And what I'll say before we get going here is the OH comes from water in step 1, and our hydride comes from this boron compound in step 2. Okay? So the mechanism for this reaction, I'm going to zoom in here to give myself more room. The first thing that happens is we end up seeing our mercury compound actually ends up sort of splitting here to give us our positively charged mercury, which is going to be playing a huge role in the reaction. Wait. And so I'm just flipping the compound around, right? It's the same one above, I just flipped it. What we end up seeing here is the alkene ends up attacking the mercury, but also at the same time, mercury will go ahead and attack the alkene, okay, just like this. And again, because mercury is such a big atom, it actually can't form this complete cyclic bond very well. So what we end up actually seeing here is not only does mercury add here like this, but it forms a partial bond with the more substituted carbon, okay, making that carbon partially positive, right? So it's kind of forming a bond, but not quite. Meaning, right, because normally when we think about doing some of these reactions, right, especially with SN2 reactions, we want to attack the site that's less substituted. But in this case, even though this carbon here is more quote-unquote substituted, it's only forming a partial bond here, it's partially positive, which makes this a great spot for our nucleophile to attack, okay? And so what we end up seeing as a result of that is this. With our water molecule here having attacked this particular site, and we end up seeing, right, this sort of reaction here. It's technically SN2, so it's wedged, right? And we see this sort of dashed position here where the methyl group is. And so what happens next is, right, with our sodium borohydride, this is actually more complicated than just having right, H- come in and exchange with mercury. So all I'm going to say here is that, right, in this last step, we actually just end up having the mercury kind of exchange with a hydrogen. We're not going to worry about anything else, right? And so that's how we get our product here. Again, don't worry too much about the mechanism, but the key thing I wanted to point out to you is why we have our OH coming in from this side here. Okay, you probably notice I didn't also go through and deprotonate it. It should be OH2 minus. But again, we won't worry about that. And in this case, right, this isn't really a chiral center, so it doesn't matter here. But one thing to note, and we'll see this a lot with these alkene reactions, is even though I had, the mercury adding right to one side here, and we made our methyl group, and hydrogen wedged, right, with mercury being cyclic underneath it, it could have come from the top too, right? So in either case, even if this was a true chiral center at the end, it wouldn't matter, right? Because we would end up having a racemic mixture of OH wedged and OH dashed. Okay. So again, don't worry about the mechanism. Just kind of worry about the reagents and what the product is. Similarly, right, instead of having H2O, if we change it with something like methanol, right, an oxygen with a alkyl group on it, we get something called an alkoxymercuration, right, which is the same exact thing, just instead of OH, now because we have the CH3 oxygen, we end up adding this ether instead. Okay, so same thing, just changing out the water for methanol, right, or it could be ethanol, right, we would have OCH3 CH2. Either way, it doesn't matter. By changing out water with this methanol, we end up getting our ether product. All right, so looking at our next reaction here, it's very similar in essence. So now this is called a hydroboration oxidation. And right, instead of having mercury, now we just have boron, right, BH3, and we have THF as our solvent. THF is tetrahydrofuran, and it looks like this, right? So it's another example of a polar aprotic solvent. But you typically see THF with boranes. And so with this reaction, right, it's another example of a hydration, right? But instead of having the OH add Markovnikov, right, to the more substituted carbon, we actually have it end up adding to the less substituted carbon, right? So very similar to our last reaction, except for now OH is adding to the less substituted carbon, okay? And that is essentially the bulk of what you need to know for this reaction. But if we're thinking about the mechanism and why this is really happening, it would be because of this, where that borane, right, BH3, it's actually interesting, the boron group here, right, because following our electronegativity rules, is actually more partially positive than the hydrogen is. So what ends up happening is the alkene will end up attacking boron, and then we actually have H minus, right, the electrons between the boron and the hydrogen actually end up attacking the more substituted carbon here. And so what we end up getting is the syn addition, right, attacking the same side of the alkene of hydrogen and, in this case, BH2, right? They're on the same side. And what happens next is another example of something being really steppy and complicated, so we're not going to show the whole thing. But in essence, what happens is BH2 ends up getting exchanged with OH. Right, so not through an SN2 attack, but through the sort of interesting exchange, which your book covers, but I won't cover here because, again, it's kind of a long 7 or 8 step mechanism. But in essence, right, BH2 just replaces itself with OH. Okay, and that's all you really need to know. So again, in essence, hydroboration oxidation, it's an anti-Markovnikov addition of alcohol. So for the last reaction here we'll cover today is the addition of halogens to an alkene. And so the general scheme for this is, right, an alkene, right, halogen represented by X. It'll basically always be Cl2 and Br2. And we end up seeing the halogen add to both sides of that alkene, right, to each carbon there. So what does the mechanism for this look like? Okay, it's going to look like this, where, right, keeping the same alkene from before, And let's say instead of X2, let's use an actual example. Let's say Br2. What we end up seeing is this interesting mechanism where the alkene, right, attacks one of the bromines. And what happens after this is the other bromine leaves. And at the same time, right, because we have the alkene attack the bromine, one of these carbons is going to end up being positively charged. So what we'll say is the bromine also attacks the other carbon at the same time. So what does this look like now? And so what we end up seeing, and I'll make these methyl groups dashed and wedged to show that there is now some 3D spatial things to worry about. We end up seeing this thing called a bromonium ion. Where, again, because bromine is this sort of large halogen, it can do this sort of cyclic intermediate. And so what happens after this, right, because you can imagine Br plus would make for a great leaving group, right, going from positive charge to neutral. The bromine that had once left now comes back in to do an SN2-like attack. Right, and we end up getting the following. Right, where that bromine comes in and attacks, pushes up those two methyl groups, and we end up getting this molecule, right? And you notice, right, because it has to do this backside attack through this SN2-like reaction, it is anti-addition, right? Bromine attacks one side, right, and the bromonium ion opens up in that way. And because bromine can attach itself to the top or bottom of that alkene, right, when we form that bromonium ion, we can end up getting a mixture of enantiomers. It didn't matter here, right, because these are both not chiral centers because there's two methyl groups, but this is a situation we might run into, and we'll see this in the lecture example. And again, right, both of these carbons are tertiary carbons, so it didn't matter which site the bromine attacked because they're equal. But just like with the mercurium ion, right, that mercury atom is so big that the more substituted side ends up being sort of positively charged. So very similarly, the Br minus, or the halogen general, will attack the more substituted site. And we'll see examples of this in lecture. Right? And following that train of thought, we see the same thing with the rate of reaction. So the more substituted the alkene is, actually the faster the reaction goes. And again, that kind of comes from the fact that we sort of have a more stable intermediate with a bromonium ion, the more substituted we have each of these sp2 carbons. So in lecture today, we'll talk about, or we'll review some of these reactions and just kind of compare and contrast them. And we'll take a look at predicting the substrates and reaction conditions to form the listed products here.